The next thing that we need to know is the derivative of a vector valued function. Suppose I have a vector valued function RT, and in this notation, it has the coordinates of f of t, g of t, and h of t. Then the derivative of r, assuming that f, g, and h are differentiable functions, they have derivatives, r prime of t is going to be the vector consisting of f prime of t, g prime of t, and h prime of t. And of course, if we use the other notation, it's going to be f prime t I plus g prime t j plus h prime t k. I define the derivative of a vector valued in this way for the case that the vectors are in R3, the three-dimensional space. In a similar manner, if R of t is in two-dimensional space, meaning that if R of t consists of two coordinates, f of t and g of t, then R prime of t consists of f prime t and g prime t, provided that both f and g are differentiable. From the geometric point of view, if in the space I have a curve, this could be two-dimensional or three-dimensional space, but we have a curve. Suppose this is x-axis, y-axis, and z-axis. And I have a curve which is in this three-dimensional space. And this is RT. Again, by RT, I mean at any point T, we have a vector RT and its endpoint will be on this curve. So at any time T or at any variable T, this is the vector RT, and that curve consists of the endpoints or terminal points of all of the vectors. One interesting thing is, in fact, that when we look at r prime of t will be parallel to the tangent to that curve at that point. So r prime of t, like in this picture, will be this vector. Of course, length depends on the components of RT. So r prime of t has its own length, r of t has its own length. So as a note, we can say that r prime of t is a tangent vector to the curve formed by r of t at the corresponding points. What does that mean? Again, in the three or two-dimensional space, suppose this is the origin. This is the curve. At any time t, I have r of t. So this r of t, the endpoints form a curve, and r prime of t is the tangent vector at the corresponding point. By corresponding point I mean the point corresponding to the terminal of the vector r of t. So this r prime of t is the tangent vector. Now let's do some examples. Let r of t be, first I give example in the two-dimensional space, then three-dimensional space. R of t is 2 sine t and e to the power of t. Part 1, find r prime of t. Obvious, this is quite simple. So I differentiate each of these two components. The derivative of 2 sine t is 2 cosine t, and the derivative of e to the t is e to the t. Part 2, find tangent vector at t equals 0. So I know that at any t, r prime of t is a tangent vector. So at t equals 0, I just look at r prime of t and compute that at 0. So I look at r prime at 0 at this given number. I computed r prime of t. It was 2 cosine of t and et, so it is 2 cosine of 0 and e to the power of 0, which is going to be the vector to 1. Cosine of 0 is 1, e to the 0 is also 1, so 2 times 1 in the first coordinate will be 2, and the second coordinate 1. So this tells me that the vector 2, 1 shows me the direction of the tangent vector at the point corresponding to the vector of r1. R0. R0 is the vector that connects the origin to the point 2 times sine of 0, which is 0, and e to the 0, which is 1. So at the point 0, 1, the tangent vector is going to be the vector 2, 1. Let me give an example of the case that it's three-dimensional. Let r of t be equal to 2t plus 1, t squared, and e to the t minus 2. Part 1, find r prime of t. This is obvious because the derivative of 2t plus 1 is 2, the derivative of t squared is 2t, and the derivative of e to the power of t minus 2 is still e to the power of t minus 2. Using the simple information from calculus 1. So find, it's the part 2, find a tangent vector at t equals 2. So when t is 2, the vector itself is 2 times 2 plus 1, 5, and then 4, e to the power of 2 minus 2, e to the power of 0, 1. At that vector, I want to find, or at the end of that vector, I want to find tangent vector to the curve that this vector function forms. So that tangent vector at t equals 2 is just r prime of 2. So in these 3 coordinates, wherever I see 2, replace it by, wherever I see t, I replace it by the value of 2. The first coordinate is just a constant. So I repeat that, 2. The second one, 2t, and when t is 2, 2 times 2, 4. And the last one, e to the power of 2 minus 2, which is 1. So this will be the tangent vector at t equals 2. From the equation of motion point of view, suppose in 2 or 3-dimensional space, again, this is the origin, and this curve shows the position of a particle. So at any time t, we have a position vector. So at any time t, this is r of t, which tells me the position of this particle. In fact, r prime of t, the vector r prime of t at any t, tells me the velocity. So if a particle is moving along this curve, so r of t, which connects the origin to that point, tells us about the position of that particle, and r prime of t is the velocity. As you know, in this context, velocity is a vector. What is not a vector is the speed. So in fact, so if r of t is the position vector, then r prime of t is the velocity vector. And the length of the vector of velocity, r prime of t, that's a length, so for any given value t, it will be a number, is the speed. So this could be a more clarifying explanation of how r of t and r prime of t are related, and also what is how the length of r prime of t is related to r prime of t. So in this context, the velocity is a vector, but the length of that is not a vector, it's just a number showing the magnitude of that vector. Similar to the first derivatives, we can talk about the second and higher derivatives. For example, if r of t is 3t squared sine of 2t and 2 cosine of 3t. Suppose we want to find the first and the second derivatives. Of course, we can go higher, but let me just keep it to these two derivatives. From the motion point of view, when r of t shows the position, r prime is the velocity, and as you know, r double prime is the acceleration. So r prime here is 6t, using, as you know, from calculus 1, using the chain rule, the derivative of sine of 2t is 2 cosine of 2t, and using the chain rule, the other one is going to be minus 6 sine of 3t. To find the second derivative, the derivative of 6t is 6. The derivative of 2 cosine 2t is minus 4 sine 2t. And the derivative of minus 6 sine 3t is minus 18 cosine of 3t. Each of these functions, each of these components are kind of calculus 1 type functions that you have seen that how we differentiate these functions. So as you see, for the vector valued functions, we can talk about higher order derivatives, first derivative, second derivative, third derivative, and so on, in a very similar manner that we did in calculus 1, but here we have more coordinates.